Welcome back, everyone. Now, I want you to think of your Cambridge physics exam like a giant, blank concrete wall in the middle of a city. To an amateur, it's intimidating. But to a master street artist, it is a canvas waiting for a masterpiece. You see, top-tier exam answers are a lot like incredible street art. You need those bold strokes of creativity and deep understanding, but they have to be backed by a rigid, reliable structure. If you just throw paint at the wall, it's a mess. Today's explainer is your strategic masterclass on Chapter 3 Dynamics, specifically linear momentum and its conservation. Whether you're tackling syllabus codes 0625, 0652, 0654, 0972, 5054, or moving up into AS and A-Level 9702, the game is exactly the same. I want to introduce you to two types of students I see all the time. First, there's Alex. Alex is brilliant, but overloads every single answer with raw physics facts and zero analysis. The examiner asks for a simple effect, and Alex writes a novel. Then there's Sam. Sam is always rushing, totally missing the command word requirements, and forgetting crucial things like vector directions. Today, we are going to look at their flawed, red-inked answers, and I'm going to show you how to transform them into perfect green-checked masterworks. Let's make your mark.
Okay, let's dive into our roadmap for today. We're covering the momentum principle, impulse and force, collision mechanics, elastic versus inelastic collisions, and then we are hitting exam question mastery. But we aren't just reading facts, we are building a physics success blueprint.
Section 1. The Momentum Principle. Defining mass in motion.
Right out of the gate, let's talk about linear momentum. It's represented by the letter P, and it's simply the product of an object's mass and its velocity. Now, this is where we need to introduce our first major strategy, command word decoding. When a question asks you to define linear momentum, Sam usually rushes and just writes mass times speed. 0 marks. Why? Because the command word define requires precision. And here's where our PELL framework comes in. Point, evidence, explanation, link. Your point is that it's mass times velocity. Your evidence is the formula, P equals mv. Your explanation highlights the absolutely critical fact that velocity is a vector, meaning momentum is also a vector quantity. It has magnitude and direction. If you write speed instead of velocity, you are instantly losing marks. And finally, your link is the unit, kilogram meters per second or Newton seconds. Always track your direction, guys. It is the #1 reason students bleed marks in dynamics. Now we hit the golden rule. The principle of conservation of momentum. The total momentum of an isolated system remains constant. This is just Newton's third law in disguise. If two isolated particles collide, the force particle A exerts on B is equal and opposite to the force B exerts on A. Because those forces are equal and opposite, the changes in momentum perfectly cancel out. Total momentum before the crash equals total momentum after. Before we continue with exactly how to apply this rule, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Let's look at a classic past paper scenario, the cannon recoil. We have a 1,500 kilogram cannon firing a 5 kilogram cannonball to the right at 70 meters per second. If Alex answers this, Alex will write out paragraphs about gunpowder and combustion. Don't do that. Let's use our Peel framework. The point: before firing, everything is stationary, so initial total momentum is 0. The evidence: the ball's momentum after firing is its mass times velocity, so 5 times 70, which is 350 kilogram meters per second to the right. The explanation: to conserve momentum, the mass of cannon must have an equal momentum of 350, but directed to the left. When we set the cannon's mass of 1,500 times its unknown velocity v equal to 350, we get a recoil of 0.23 meters per second. Simple, structured, full marks.
Section 2. Impulse and force. Time changes everything.
Impulse is where we see the transformation happen. It's the product of a constant force and the time interval over which it acts. But here is the secret weapon you need for your exams. Impulse is exactly equal to the change in momentum of the object. It's just Newton's second law rearranged. The unit is the Newton second. This is your go-to concept whenever you are analyzing short-duration collisions, and the command word asks you to calculate or determine the average force. Let's see how our students handle this.
All right, welcome to Challenge 1, the data scan. You have an exam question featuring a 60-gram tennis ball being served at 55 meters per second. The contact time is 25 milliseconds. Imagine a 60-second timer ticking down. What is the core trend you need to extract here? Sam usually misses the unit conversions. 60 grams is 0.06 kilograms. 25 milliseconds is 0.025 seconds. If you don't convert, your red pen marks are staying red. But if we apply our structural framework, we find the change in momentum, mass times velocity, giving us 3.3, and divide it by that tiny time interval. The result is 130 newtons of average force. Look at how a structured approach transforms a messy, rushed answer into a perfectly calculated green-checked solution.
Let's lock this in with a golf example. A 45-gram ball driven at 40 meters per second with a contact time of just 3.0 milliseconds. Notice how dramatically the contact time dropped? Because the time in the denominator is so tiny, the average force required spikes massively. This is the exact kind of proportional relationship examiners want you to explain in follow-up questions. And hey, stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 3. Collision Mechanics. The 3-step strategy. If you want to absolutely guarantee top marks in collision math, you must follow this 3-step blueprint. Step 1. Draw a labeled diagram. Visualize the before and after, and explicitly assign positive and negative directions. Step 2. Obtain expressions for total momentum. Remember the vectors. Step 3. Equate the momentum before to the momentum after. I literally see students drop a whole grade boundary because they skip step 1. They think they can do the vector math in their head. Sam does this constantly, and the negative signs just vanish. Draw the diagram. It's your structural scaffolding.
Section 4. Elastic versus inelastic. Where does the energy go?
Welcome to Challenge 2, Find the Flaw. I'm going to read you a sample paragraph from Alex. In an inelastic collision, the objects stick together, so both kinetic energy and momentum are lost to the environment as heat and sound. Did you catch the sentence losing marks? It's the claim that momentum is lost. That is a massive misconception. In perfectly elastic collisions, kinetic energy is fully conserved. The relative speed of approach equals the relative speed of separation. But in inelastic collisions, like clay squelching on the floor, kinetic energy is lost to heat, sound, or deformation. However, momentum is absolutely always conserved in an isolated system. Never let an examiner trick you into saying momentum is lost.
Section 5. Exam Question Mastery. Testing our framework.
All right, it's time for Challenge 3, Speed Writing. We are looking at a classic Cambridge inelastic embed problem. Question 24. We have an 85-gram block moving left at 2.0 meters per second. A 4.0-gram steel ball is fired right at 45 meters per second and embeds into the block. We need their common final speed. Imagine a 30-second timer on your desk. How do you construct the perfect full-mark mathematical paragraph without overloading or rushing? Let's break it down together.
We apply our 3-step blueprint. Step 1, assign direction. Let's make right positive. So the ball is positive 45, but the block is moving left, so it must be negative 2.0. That negative sign is the trap. Sam always misses it. Don't be like Sam. Step 2, initial momentum. Convert to kilograms. We get 0.004 times 45 plus 0.085 times negative 2.0. Step 3, final momentum. Since they embed, combine the masses. That's 0.089 kilograms multiplied by our common velocity, v. Equate step 2 and step 3 and solve. When you use this system, you turn a complex paragraph of text into a simple algebraic lock that clicks open every single time.
Let's crank up the difficulty. Question 15 is a 2-dimensional vector problem. A 45-gram ball hits a wall at 12 meters per second at a 30-degree angle and rebounds at the exact same speed and angle. Contact time is 15 milliseconds. What is the force? When Alex sees this, panic sets in. There are angles, speeds, times. It looks like a mess. But remember our street artist analogy. We need rigid structure. We need our time management matrix and our data extraction tools to isolate exactly what matters.
So you systematically extract the variables. Mass is 0.045 kilograms. Time is 0.015 seconds. Now for the velocity. Because the ball hits at an angle, the momentum change only happens on the axis perpendicular to the wall. The velocity parallel to the wall doesn't change at all. So you use your vector decomposition, sine or cosine depending on the angle placement, to find just that perpendicular component. Multiply by mass to get your initial and final perpendicular momentum, find the change, and divide by time to get your force. By categorizing the data first, you don't waste time calculating things the command word didn't ask for.
Here is one more timeline scenario. Question 22. A steel ball falls from 192 meters. At 0 seconds, acceleration is exactly 9.81. But as it falls and hits 40 meters per second, air resistance becomes a major factor. The exam gives you a graph. You have to read the air resistance at that specific velocity, subtract it from the weight to get the resultant force, and use F equals ma to find the new, lower acceleration before impact. This tests your ability to adapt your framework to a changing timeline. It's not just plugging in numbers, it's understanding the narrative of the physics over time.
Let's recap the ultimate physics success blueprint. These are the rules that guarantee top marks. Rule 1. Command word decoding. Always explicitly assign and state your vector directions based on what the question actually asks. Rule 2. Apply the Peel framework and the F delta T equals delta P impulse equation for any impact scenario. Rule 3. Time management and the three-step diagram method. Structure your math so you never get lost halfway through an equation. And of course, assume momentum is always conserved. Listen to me, students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
I want to leave you with one final mind-bending thought experiment. We talked about that inelastic lump of clay hitting the floor and squelching. It loses all its kinetic energy. It completely stops. But we know momentum must be conserved. It had downward momentum before the crash and 0 after. So where did it go? The secret is that the Earth and the clay are the system. That momentum transferred to the entire planet Earth, changing the planet's velocity by an unfathomably small, unmeasurable amount. The math proves it. I want to hear from you. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.